Hi, in the previous truss element stiffness matrix videos, we have developed the stiffness matrix for the truss elements. In this video, we're going to show you how to use that matrix. Okay, please take a look at the figure here. We have a truss example. We have a two rod, which is a mount along the wall, and then the other end is tied together. Okay, a force is acting to the node to the negative x-axis, and also a downward displacement is acting on one right here. Okay, both rod have the same cross-sectional area and same materials, same elasticity. Okay, one rod is a 4 meters long. The other one we don't know yet, but the distance between the two nodes, node 2 and node 3, is 3 meters. Okay, so the problem is asking you what is the nodal displacement for node or node, the nodal force acting on it, and the axial force and stress along the rod. Okay, now the first step, always we change all the units into something workable. Okay, because you know what, centimeter square and GPA, they don't get along very well. We change everything into meter square and Pascal. Okay, with that we have two K values. Okay, again, the K values is you get it by EA over L. EA over L. By the way, if you know the distance between node 1 and 3 is 4 meters, 2, 3 is 3 meters, the distance between nodes 1 and 2 has to be 5. Okay. Now the step 2, we name the elements. Okay. We name the elements 1 and 2. You can name them the other way around, but as long as it's consistent and you work along with it, it's fine. Again, we name the nodes, nodes 1, 2, and 3. You can name it anything you want as long as you're consistent. Then for this truss elements, right, I like to set up an information table so it's easier for me to work with. Okay, we need to set up an information table. Okay, let's go over the first elements. Elements 1, which is going has two nodes, nodes 1 and 2. The angle for element 1 we don't know, but we don't need to know that because all we need to know is the ratio along the length, cosine and sine of it. The k values we get that from the previous equations. Okay, cosine for the element 1 is -4 over 5. Okay, because we're traveling from node 1 to 2. Remember, the order is so important here. Node 1 to 2 is -4 over 5. Sine is a +3 over 5. So if we know cosine and sine, we know c squared, cs, and s squared. Okay. Elements 2. Node is traveling from node 1 to 3. Okay. And the theta, we know this time, is 180 degrees. Okay. K, we just bring that terms. Okay. Cosine 180 is -1, sine 180 is 0. So if we know c and s, we know c squared, cs, and s squared. So with this table, it's very helpful, nice and clear. So we have this cs, c squared, and s squared term. We just substitute into the transformation matrix that we developed previously. Now we want to add these two matrices together because they have a common node. This portion of it looks after node 1, and the other portion handles all the information in node 2. For that stiffness matrix, the first portion looks after node 1 and all other stuff looks after the node 3 information. So we add the common nodes together. Okay. By the way, what I did here is have a common multiple, it's a scalar. We just factor out the terms so I can add it together. If these two numbers are not the same, you cannot add it together. Okay. So we have that we bring this term down. Okay, and we try all the additions. Okay. For this portion, these four values, these four entry points, 47.25 is contributed by 16 plus 31.25. You get this term. Negative 12 is basically negative 12 plus 0 here. We do the same thing for second node. We bring it down right here. That term goes to here and this term goes to here. Okay, then we look after the second matrix here. We bring all the x as all the three terms, everything related to node 3 we put here. We don't put anything here because we have nothing, no terms related to this. Okay. So from the 4 by 4 matrix, now we have a 6 by 6. Okay, and we have a force vector which would involve 6 values. Okay, and we have same thing, displacement vectors with 6 values. Now we apply the boundary conditions. U1x is something that we are looking for. U1y is negative. Remember, that thing's dropped by 5 centimeters, right? So U1y is negative 0.05. U2 and U3 is stick along the wall, so all values are zeros. Okay. On the left side, F1x is a negative 1 times 10 to the 6. Remember, that thing is what? 1,000 kilonewton to the left. So the sign is so important. It's negative 1 times 10 to the 6. F1y and all other forces is something that we're looking for. So after I apply the boundary conditions on the force vector and the displacement vector, I turn the 6 by 6 matrix into 6 equations. Here we go. And then with 6 equations and 6 unknown, we can solve for each unknown here. Now, right here is a summary of all the unknowns. Okay, now we have all 6 the force vector with 6 entries and the displacement factor in the 6 entries as well. And then the next step, I draw total free body diagrams. Nothing fancy. I just write down the force into each node and the directions of it. Okay. And with this in mind, we can draw the free body diagrams for each element here. Okay. Okay, note. This is the force acting in the global reference frame. Okay. Our job is to turn that into the F hat reference frame. So we know these are the force acting along the rod. As you can see, along the rod, nothing is acting in a y direction because all the force is acting axially along the rod. So we know the rod is under a tensile force of 72.72 kilonewtons. Okay, and we all know force over area is a stress, and we can calculate stress based on the numbers here. We do the same thing for the elements 2. We draw an individual free body diagram for that elements 2, and then we know that the compression force is acting on it, and divided by the cross-sectional area, you get a stress for the axial stress for elements 2. Okay, thank you very much.